We're now differentiating trigonometric functions. So if you look at page 25 of the log tables, you will see this page. All of these functions here are then derived, and you get back your f dash x here. Okay, so we're focusing on these at the moment, the trig functions. Okay, so cos x, the derivative of cos x is minus sine x, the derivative of sine x is cos x, and the derivative of tan x is sec squared x. So again, if you look at the graph, if we draw out sketch the graph of sine x, alright, and if you put in a tangent at the turning points and at the points of inflection, you can see that the sine function actually resembles the cosine function. Okay, so that's why it ends up looking like the cosine function. So when you get the derivative of sine x, it is the slope of the function at tangent to the curve, alright, and you get the corresponding cosine function. Okay, so that's just where it comes from. It could come up in the papers, you know, what's the geometric relationship between the sine function and the derivative of the sine function, and you might talk about the tangents to the curve. Their slopes correspond to the points on the cosine function where it cuts the y and the x-axis. Okay. Right, let's look at 13.18. Use the chain rule to differentiate the following with respect to x. So part 1, f of x is equal to cos 4x. So here it's just a cos 4x to the power of 1. So we can let our u equal 4x, and we let our y equal cos u, which is what I've done here in the black boxes. Go off and get dy du. So the derivative of cos is minus sine. So dy du is minus sine u, and du dx is 4. Put it into the chain rule formula. Dy dx is equal to dy du multiplied by du dx. So dy du was minus sine u multiplied by du dx, which is 4. And then just rearrange it, and you'll get minus multiplied by 4 is minus 4 sine 4x. Again, substitute back in for u. U was 4x. That's using the chain rule. Obviously, if we use the quick method, so if we look over here to the right hand side, we have y is equal to cos 4x. So differentiate the function first, okay, the trig function. The derivative of cos is minus sine. So you get minus sine 4x, and then you have to derive the angle. The derivative of 4x is 4. Rearrange it, and it becomes minus 4 sine 4x. So that's the quick method. Differentiate the trig function first, and multiply it by the derivative of the angle. Okay. Part 2, g of x is equal to tan 3x to the power of 4. Now, this one is slightly different, okay? So, instead of letting u equal the angle this time, we have to let u equal tan 3x, and it's because of the power of 4. So if we look over here, g of x is equal to tan 3x to the power of 4. Rewrite that as tan 3x all in a bracket to the power of 4. Okay? And here, this is where we just use our normal chain rule. Okay? So let u equal the bracket to the power of 4. Or sorry, let y equal u to the power of 4. And let u equal the bracket. So u is tan 3x. Okay? So u is tan 3x and y is u to the power of 4. Get the derivative of y, so dy du comes out to be 4u to the power of 3. Put that in a box. Then get the derivative of u. So u is tan 3x. The derivative of a tan function is sec squared. So tan 3x then derives into sec squared 3x. And then you have to get the derivative of the angle 3x as well. So you derive the function, which is tan, okay, and that becomes sec squared 3x. And then you have to multiply it by the derivative of the angle as well, which is 3. Lastly, then, you can just put the 3 in front of sec squared 3x, and you get 3 sec squared 3x. Next, then, substitute dy du and du dx into your chain rule formula. So dy dx is equal to dy du multiplied by du dx. And you get 4u cubed by 3 sec squared 3x. Substitute back in for u, and we get tan 3x there, okay? So it's 4 times tan 3x cubed by 3 sec squared 3x. Let's tidy this up now. What I'm going to do next is I'm going to multiply, because they're all multiplied together, I'm going to multiply the 4 by the 3, and I'll get 12, okay? Tan 3x cubed can be rewritten as tan cubed 3x multiplied by sec squared 3x. Okay, and that's your answer. So 12 tan cubed 3x sec squared 3x. Part 3, get the derivative of h of x with respect to x. Okay, so h of x is equal to the root of sine x. rewrite, get it out of the surd, rewrite it as sine x to the power of a half. So let u equal the bracket, so u equals sine x, and y is equal to u to the power of a half. Okay, dy du then is going to be a half times u and reduce the power by 1, so you'll get minus a half. And du dx, the derivative of a sine function, is cos function. Okay, then substitute your dy du and your du dx into your chain rule. So dy dx is equal to dy du multiplied by du dx. And you'll get out the first line up here. So a half times u to the power of minus a half by cos x. Next, just employ your rules of indices. So you don't want to have that negative power on the u, so flip it and put it as a positive power. So it'll be 1 all over 2 times u to the power of a half, still multiplied by cos x. Substitute back in for u, so u, remember, was sine x. So it's going to be 1 all over 2 times sine x to the power of a half multiplied by cos x. So now I'm just multiplying 1 by the cos x here, and I'll get cos x all over 2 times anything to the power of a half is the square root of. So it's cos x all over 2 times the root of sine x. Now we're going to use the quick method for the next one, okay, because you know now how to use your chain rule. So let's say the function g of x is cos 3x to the power of 4. Just rewrite that as cos 3x all in a bracket to the power of 4. Okay, now we're going to use the quick rule. So g dash x, so dy dx is equal to, bring down the power in front of the bracket. So 4 times cos 3x and put the power, reduce the power by 1, so you'll get a power of 3. Then you have to differentiate inside the bracket. Okay, so I am differentiating the cos 3x inside the bracket. So when you're differentiating a cos 3x, remember you have to differentiate the trig function first. The derivative of cos is minus sine. So that's minus sine 3x. But then remember, lastly then, you have to derive the angle. The derivative of 3x is 3. Then tidy that up. Everything is being multiplied together. So 4 times 3 is 12 times the cos of 3x to the power of 3 can be rewritten as cos cubed 3x. And sorry, there should be a minus in front of that as well because it was minus sine 3x multiplied by sine 3x. Okay, so that's your answer. Minus 12 cos cubed 3x sine 3x. That's using the quick method. Again, if you want to use the chain rule for that, we're going to let u equal cos 3x, and therefore y will equal u to the power of 4 because it was cos 3x to the power of 4. Du dx is going to be minus sine 3x, and then remember you have to derive the angle as well, so that's multiplied by 3. We can put that in a box. You can bring the 3 in front as well, obviously then. Then let's get the derivative of y with respect to u, and you get 4 times u to the power of 3. Okay, so we now have dy dx and du, we now have du dx and dy du. Put it into your chain rule formula. So dy dx is equal to du dx, which is minus, I'm just going to put the 3 in front, minus 3 sine 3x by dy du, which is 4u cubed. Then I am going to substitute back in for my u, so minus 3 sine 3x times 4, and u was cos 3x to the power of 3, tidying that up. Minus 3 multiplied by 4 is minus 12 sine 3x, and cos 3x to the power of 3 is cos cubed 3x. Okay, so minus 12 sine 3x cos cubed 3x. The order doesn't make a difference, they're all being multiplied together. So that's using your chain rule approach. Obviously, the quick method is quicker. Now the next function, so we want to differentiate f of x with respect to x. Now if you look at this, so the function is x times sine x. This is going to have to be the product rule, where it's u multiplied by v. So u is x, and v is sine x. Okay, so remember your formula now for the product rule. Dy dx is going to equal u times dv dx plus v du dx. So we need to get out our dv dx and our du dx. So I said u was equal to x, therefore du dx is 1. Put that in a box. I said v was sine x, so therefore dv dx, the derivative of a sine function is a cosine function. Put that in a box. And now we can insert that into our product rule formula. So dy dx is going to equal u. U I said was x. So u times dv dx, we have now got to be cos x. So that's x times cos x plus v we said was sine x. Du dx was 1 times 1. Alright, so tidying that up, you get x cos x plus sine x. Okay. Now, if you look at page 355 of the books, worked example 13.20, that's what I've just done there. But there's a second part to that question. It said, hence, find the slope. So this is the slope, isn't it? It's the derivative of the function. So that is the slope there, dy dx. But it said, find the slope of the tangent to the curve f of x at the point pi 0. Okay, so obviously we're dealing with a trig function, so it's going to be in radians. So if we have found the slope, which we have, okay, so your dy dx is your slope. So we now want to get the slope as a particular value. So here's my slope. I'm going to sub in for x. So x is pi, so just be careful when you're substituting it in. So dy dx, or the slope if you want to call it, doesn't make a difference, is going to be pi times cos pi plus sine pi. Okay, that works out to be cos of pi is -1, so that's pi times -1 plus the sine of pi is 0, so that just works out to be minus pi. Okay, so the slope of the tangent to that curve f of x at the point pi 0 is minus pi. That is the slope, and it's in radians. Okay, worked example 13.21 is next. Let f of x be the function sine x to the power 4 plus cos x to the power 4. It says find the derivative of f of x and then express it in the form k times sine px, where k and p are elements of the integers. So we're going to differentiate it first and then we'll express it in the form they want it in. So we have two functions together, okay, added together. So again, we're just going to differentiate them separately and then add them together at the end, okay? So the derivative of sine x to the power 4. So I'm going to do the quick method. So bring down the power in front, it becomes 4 times the bracket, which will be sine x to the power of 3. Okay, reduce the power by 1, so you get a power 3. Then differentiate the function. The derivative of a sine function is cos. Lastly, then differentiate the angle. Well, the derivative of x is 1. Okay, so that just tidies up to be 4 sine cubed x cos x. Then over onto the right hand side, we want to now differentiate cos x to the power 4. So again, bring down, I'm going to do the quick approach, bring down the 4 in front and multiply it. Okay, so you get 4 times cos cubed x, so I reduced the power by 1 and I got it cubed. Then differentiate the trig function. So the derivative of cos is minus sine x. Okay, and lastly then derive the angle. The angle is x, the derivative of x is 1. Tidying that up, I'm going to multiply the minus by the 4 and you get minus 4 times cos cubed x by sine x. Okay, so that's the derivative. I can't tidy that up anymore. So I found the derivative, but now they want me to express it in the form of k times sine px, where k and p are elements of z. So if you look at that function, I do not want to have any cos in my function, so I'm going to try and get rid of it. Now, I've got sine cubes. I don't want a sine cubed in it either. Okay, so you're going to have to use your log tables, all right? So you should have page 7 and 8, 7, 8, 9, or whatever pages they're on. Not 7, 8, 9, page 14 and 15, sorry, of the log tables open to see what we can use. Well, first of all, because there's no formula in the log tables for a sine cubed or a cos cubed to get rid of it, I'm going to factor out what's common to both sides. Okay, so if we look at both of them, they both have a 4, right? So I'm going to factor out 4. They both have a sine, don't they? Sine x. And they both have a cos x. So I'm going to factor out sine x cos x. And I'm going to open my bracket. So if I look at the left hand side, if I have factored out 4 sine x cos x, I am left with sine squared x. And on the right hand side, 4 sine x cos x divides into minus 4 cos cubed x sine x minus cos squared x times. Now, so let's look at this, what I've simplified out. Remember, all the while, I don't want to have any cos in my answer, okay? So I need to look at this here first. Go to page 14 of the log tables. Do you see any formulae, okay, where you have a cos of the angle by a sine of the angle? So cos A, sine A, anywhere. It doesn't matter if there's a coefficient in front of it, just can you find one? You should find the formula sine 2A equals 2 sine A cos A. Okay, this was the part I was looking for. Sine angle, cos angle. Alright? Now, that's the same as sine 2A. Okay? So, the only thing that's different, if I look at mine, I've got 4 sine x cos x. Alright? How would I turn that into 2 sine x cos x? Well, couldn't I factor out 2 out of that? And I could rewrite it as 2 times 2 sine x cos x. Okay? Or you may not have realised that you could factor out the 2 out of it, and you might have just seen that, well, look, if 2 sine A cos A is equivalent to sine 2A, well then wouldn't 4 sine A cos A be equivalent to 2 sine 2x? Okay, you could do it that way as well. It doesn't really make a bit of difference. Okay, or if we had gone with the first one, which I never finished out, you'd have it written as 2 times, and then you'd have seen that it's sine 2 times A, or 2 times x, sorry. Okay, same thing either way. So I now know that this can be rewritten as just in sine. Okay, so 4 sine x cos x is now the same as 2 sine 2x. Okay, so I'm just going to sub that in now. So I'm going to sub this in for this. Okay, so I just rewrote the function up on top, and I'm subbing in for 4 sine x cos x, and I get 2 sine 2x by the bracket. Now, we have to look at this bracket. So, if you look into your log tables on page 13, okay, look for a formula there where 13, 14 or 15, look for a formula where we're looking for sine squared x minus cos squared x. Something that looks similar to that. Okay, the only one that you can see there on page 14 that has a cos squared x and a sine squared x minus a sine squared x is the first one. Cos 2a is equal to cos squared a minus sine squared a. Okay, now I know you're going to say, but that has a cos in it, and we wanted to get rid of cos, but we'd eventually get rid of it. Alright, so we're going to use that knowledge, and we're going to sub in. So now, my bracket here, alright, I'm going to switch it in for this, but look, the signs are different, so we're going to have to do something with the signs. I want it as a cos squared x minus, sine squared x minus cos squared x. So down in my formula, all that's different is the signs. So I'm going to multiply everything across by minus 1. And then that'll become minus cos 2a minus cos squared a plus sine squared a. And now I have it the way I wanted it. I have a sine squared a minus a cos squared a. And that equals minus cos 2a. So now we can substitute in for the black bracket, okay? So instead of sine squared x minus cos squared x, I'm now going to put in minus cos 2x, okay? So I'm substituting in for the bracket, and I'm putting in minus cos 2x, and then I'm just going to simplify it, and I get minus 2 sine 2x cos 2x, alright? Again, bear in mind all the while, we want to just have sine in our answer. So now you're going to look into your log tables. Again, you're going to look at page 14, and you're going to look for well, we've actually already used the exact same rule already. Okay, you're looking for a sine of the angle, 2 times sine of the angle by cos of the angle. You should note that it is the formula sine 2a, we've already used it, is equal to 2 sine a cos a. Okay, so the sine of twice the angle will equal the sine 2 times the sine of the single angle by the cos of the single angle. Now, all you should notice here is that there's a slight little difference. So we know we're going to use this formula, but if we look at our last line, which is this one here, we've got twice the angle, whereas in the formula, it's the single angle. Okay, twice the angle, and they have the single angle. So if 2 sine A cos A is equivalent to sine 2A, well then wouldn't 2 sine 2A cos 2A equal the sine of 4A? Alright. So, just bearing that in mind again, we knew we could use that formula because I have a 2 times, even though it's minus 2 times, I have 2 times sine of an angle by the cos of an angle. So I can use the formula. But you just have to note that the formula is 2 sine of the single angle, cos of the single angle, whereas we've got 2 sine twice the angle by cos twice the angle. So remember, that's going to be sine 4 times the angle. Alright, so now we can substitute in. So what am I subbing in for? I'm subbing in for 2 times the sine of 2x cos 2x, and I get minus sine 4x. Okay, and now I have it written in the format of k times sine px, where k will be minus 1, p is obviously 4. Right, next I want you to go on to page 355 and mark the following questions. Okay, if you look at the questions 9, 15 and 16, you don't have to do them. I want you to just watch the video on how to do them. But the rest I want you to sit down now, do those questions out and pause the video as you go along to look at the solutions. Okay, so exercise 13.6, question 1. Get the derivative of sine x plus cos x. You should have gotten out cos x minus sine x. For part 4, 4 sine theta minus 8. You should have gotten out 4 cos theta. And remember, minus 8, it's a constant. It goes to 0. So you just get 4 cos theta. Part 5, 2 cos x minus 3 sine x. You should have gotten out the derivative to be minus 2 sine x minus 3 cos x. Question 2. Get the derivative, well, it says find the gradient of the curve. The gradient is another word for slope, and slope is another word for derivative. So get the derivative of the function. So for part 2, we were looking for the derivative of sine x when x is equal to 0. The derivative of sine x is cos x. Okay, so that's where we are here. And you're looking for that slope when x is equal to 0. Sub in 0, and you should get out a slope of 1. For part 4, the derivative of minus 2 sine x. You should have gotten out minus 2 cos x. And then sub in when x is equal to pi over 4. Use your log tables, page 13, okay, and you'll get out the number there. Simplify it, so you'll get minus 2 out over root 2, but that can be simplified down to minus root 2. Okay, so just watch that, minus 2 all over root 2. That's the same as writing minus root 2 all over root 2. Those root 2's cancel and you're left with minus root 2. Okay, part 5. Y is equal to x minus sine x. So again, differentiate the function. The derivative of x is 1. The derivative of minus sine x is going to be minus. The derivative of sine x is cos x. Then when x is equal to pi over 2, sub it in, you should get out a slope of 1. Question 3. Find the equation of the tangent to the curve y at the point where theta is equal to pi over 2. Okay, so the equation of a tangent, you need a point and you need a slope. Well, first of all, we'll get out the slope, right? So we're looking for dy d theta, right? So we're differentiating y with respect to theta. And you should get out minus sine theta plus 3 cos theta. That's your derivative, which is your slope. They said find the slope when theta is equal to pi over 2. So sub in for theta, and you should get out a slope of minus 1. So I now have my slope, which is m. Next, you need to get the point. So in order to get the equation of the tangent, well, if theta is equal to pi over 2, to get the corresponding y value, you need to sub pi over 2 into your original function. So sub in pi over 2 into y, and you'll get back y equal to 3. So therefore the point is pi over 2, 3. So you now have a point, and you have the slope. Therefore you have the equation of the line. So the equation of the line is going to be in terms of theta and pi. Alright, and you'll get out y is equal to minus theta plus 3 plus pi over 2. Question 4. Use the product and the quotient rule to differentiate the following functions. Well, we've done the product and the quotient rule. So part 2, g of x was x squared sine x. So that's a product rule, u by a v. Okay, so that's down here, this one here. Okay, so again, u multiplied by v, use your product rule. The product rule is dy dx is equal to u dv dx plus v du dx. Alright, so u is obviously your x squared, v is your sine x. You go off then, you get that out and sub it back into your formula. So this was u, this is dv dx plus v du dx. Tidy it up, and they factored out x at the bottom because it was common to both. I suppose you don't necessarily have to do that. They didn't ask you to do it, but you know, if you want to give something in its simplest terms, you'd factorize out where you could. Okay, so you factor x out and you'd be left with x cos x plus 2 sine x. Part 3, x tan x. Again, that's a product rule, u by a v. So it's going to be x is u and v is tan x. Sub it into your product rule formula. So that's going to be u, the derivative of tan x is sec squared x, plus v by du dx. Okay, the derivative of x is 1. Tidy it up and you get x sec squared x plus tan x. Part 5. Part 5 is the quotient rule, u over v. So u is 4x and v is going to be cos x. Okay, so when you get the derivative of h of x, it's going to be v du dx minus u dv dx all over v to be squared. Alright, tidy that up. You'll get 4 cos x. A minus by a minus is a plus 4x sine x all over cos squared x. Up on top then 4 was common to both, so they factored it out. So 4 a bracket cos x plus x sine x all over cos squared x. The only reason they really factored out is just to see if anything would divide above and below in the numerator and the denominator. And if you don't factorize out, possibly something might simplify and you wouldn't have spotted it. So that's why, you know, if you can factor out something that's common on the top, do, or if it's common on the bottom, do if you can. Question 5, find the derivative of each of the following functions. So part 3, h of x was 7 tan 5x. Okay, so again, off you go. This is just the normal differentiation. So it's tan 5x to the power of 1, isn't it? So 1 times 7 is 7. Differentiate tan 5x, you'll get sec squared 5x. Alright, and then differentiate the angle, which is 5x, and you'll get 5. But remember, 5 then multiplied by the 7 in front is 35. Okay, if some of you are finding that one hard to follow, I'll just do it quickly here. So 7 tan 5x. Alright, you can treat that as to the power of 1. So 1 by the coefficient, so you're going to get 7. Okay, by the derivative of tan 5x is going to be sec squared 5x. And then last you have to derive the angle, 5x, and you get 5. Then 7 by 5 is 35, so that's where its 35 is coming from. Part 4, f of x is 2 sine 3x plus 5 cos 2x. Again, just differentiate them separately, add them together. So the derivative of 2 sine 3x is going to be 2 cos 3x, and then you have to derive the angle, and you get 3. Okay, so I'll just squeeze it in up on top. So you would have had 2 sine 3x, but then that gets multiplied by the derivative of the angle, which is 3. Okay, 3 2s are 6, so that's where that 6 is coming from. 6. Sorry, that should have been cos when I was deriving the angle. That should be a cos there. Okay, so 2 cos 3x by 3, and you get 6 cos 3x. Then over onto 5 cos 2x. So again, it's going to be 5 times the derivative of a cos function is minus sine function. So that's minus sine of 2x, and then you have to derive the angle, and you get 2. 2 times 5 is 10, and 10 multiplied by a minus is minus 10. That's where that's coming from. So minus 10 sine 2x. Part V, g of x is tan 2x plus tan 3x. So again, the derivative of a tan function is sec squared. So that's going to be tan 2x goes to sec squared 2x, and then you have to derive the angle, and that's where the 2 is coming from in front. Plus, the derivative of tan 3x is sec squared 3x. Again, you have to derive the angle then, and you get 3. Question 6. Find the derivative of each of the following functions. Part 2, g of x is tan squared x. So again, that's the same as writing g of x is equal to tan in a bracket to be squared. Tan in a bracket to be squared. Okay, I can't really fit that in, but anyway, you know what I'm saying. Alright, the Then bring down the power in front of the bracket and you'll get 2. Multiply by the bracket tan x, reduce the power and you get tan x to the power of 1. Then differentiate the trig function, so tan x goes to a sec squared x. Lastly, then differentiate the angle, the derivative of x is 1, so you just get it multiplied by 1. So that's 2 tan x sec squared x. Part 3, h of x is cos cubed 5x. So again, that's the same as writing cos 5x to be cubed. The derivative of that is going to be 3 times the bracket to the power of 2. Derive the trig function, the derivative of cos is minus sine, so that's minus sine 5x. And lastly, derive the angle, which is 5x, so you'll get 5. Then tidy it up. Okay, and that's how they're getting minus 15 cos squared 5x sine 5x. Last one, part 4, sine squared 2x plus cos squared 3x. Again, just do them separately. Okay. Right, so sine 2x in a bracket to be squared, that's 2 times the bracket to the power of 1. Okay, anything to the power of 1 is just itself. Then derive the trig function, so the derivative of sine is cos 2x, and the derivative of the angle 2x is 2. Alright, so tidy that up, you're going to get 4 sine 2x cos 2x. Alright, then do it for the other bracket. Cos 3x to the power of 2, the derivative of that is going to be 2 times the bracket to the power of 1, anything to the power of 1 is just itself, times derive the trig function, cos 3x is going to turn into minus sine 3x. Then derive the angle, the derivative of 3x is 3. So you're multiplying 2 by minus 1 by 3, and that's how they're getting minus 6. So minus 6 cos 3x sine 3x. Okay, so that's this line here. Then they factored out 2, it was common to both, and they got 2 sine 2x cos 2x minus 3 by 2 sine 3x cos 3x. And then if you notice down in the last line, they're using the following formula from the log tables. 2 sine a cos a is equivalent to sine 2a. Okay, and we have 2 sine 2x cos 2x. Alright, so our angle is doubled. So therefore here our angle has to be doubled as well, and we get 4a. So they're getting 2 times, the 2 was in front of it. Okay, that 2 there was in front of it. The bracket becomes sine 4x. Okay, and it's the same over on the other side. Right, here I've got 2 sine a cos a, don't I? So again, the formula, sine 2a is equal to 2 sine a cos a. So if I change the angle there, they have an angle of 3x, so 3 times the angle means it's 3 times the angle over here, and that becomes a 6a. Okay, so that's how they're getting minus 3 sine 6x. They just tidied it up. So where you see that you can use a trig identity, use it. Question 8. Given that the d dx of sine x, so the derivative of sine x is equal to cos x, and the derivative of cos x is equal to minus sine x, find the derivatives of each of the following using the quotient rule. Okay, you know the quotient rule is a u divided by a v. If you look at any of those there, none of them are in a fraction format. None of them are u over v, are they? So we need to turn them into it. So, part 1, sec x. Look at page 14 of your log tables. And on page 14 of the log table, page 13 of the log tables, you'll see that sec a is equivalent to 1 over cos a. Okay? So therefore sec x is equivalent to 1 over cos x. That's coming from page 13 of the log tables. So now we want to get the derivative of that. Well, now we have it as a u over v. U over v. Okay, so use your quotient rule. V du dx minus u dv dx all over v squared. So v is cos x, so it's cos x v du dx minus u dv dx all over v squared. Tidy it up, you'll get out sine x all over cos squared x. Now what they did here was they factored out 1 over cos x. Why? Because you know that sine over cos x will give you a tan x. Okay, so if you can factor something out, do. So we now have sine x over cos x multiplied by 1 over cos x. Okay, sine x over cos x is your sec x, is your tan x, right? So that is tan. And 1 over cos x, we already know, is sec x. So that's why we have now written it as sec x tan x. Part 2. Again, tan x is the same as sine x over cos x. That comes from page 13 of the log tables. So if we want to get the derivative of that using the quotient rule, that's a u over a v. So v du dx minus u dv dx all over v squared. So that's quotient rule. Tidy it up, so cos squared x plus sine squared x all over cos squared x. Remember, from the log tables, page 13, cos squared a plus sine squared a is 1. So that becomes a 1 all over cos squared x. Alright, and remember that can be written as 1 all over cos x by 1 all over cos x. And we already know that 1 over cos x is 1 over sec x, or sorry, not 1 over. 1 over cos x is sec x multiplied by sec x. And we get sec squared x. Part 3, cot x. Okay, so again, if you look at page 13, cot a is equal to cos a over sine a. So therefore, cot x is equal to cos x over sine x. Again, we now have a u over a v. So we use our quotient rule. V du dx minus u dv dx all over v squared. Tidy it up. And what they then did, they tidied it up and they factored out minus 1 outside the bracket. So you've got a minus by sine squared x plus cos squared x all over sine squared x. The reason they factored it out is because we already know that sine squared a plus cos squared a is 1. So that's how they're getting minus 1 all over sine squared x. Okay, next we'll look at the log tables, page 13. Cosec a is equivalent to 1 over sine a. So minus 1 over sine squared x is the same as writing minus 1 over sine x by 1 over sine x. So again, that's minus 1 over sine x is the same as cosec x. So it's cosec x multiplied by cosec x, which is where they're getting minus cosec squared x. Okay. Question 10. Find h dash x, the derivative of the function. Okay, so again, you'll see h of x is a u over a v. So put down your quotient rule. Alright, u is sine x, v is 1 plus tan x. Therefore, du dx is cos x, dv dx is going to turn into sec squared x. Then put it all into the formula. So I've got v du dx, and then minus your u dv dx all over v squared. Tidy it all up, multiply it all out. You'll get your next line. Okay. Tidy it up further. If we could try and get it all into, costs and sines or whatever, and we'll try and get rid of the tan out of it. So you can see there we've got cos x plus cos x tan x. Well, tan x, if you look at page 13, is the same as sine x over cos x. So I've substituted it in green there. Minus sine x, sec squared x. All over 1 plus tan x, all to be squared. Tidy that up further. So you can now see when I substituted in the green bracket, sine x over cos x, won't cos x divide into cos x and you're left with sine x. Okay, so on the next line you've got cos x plus sine x minus sine x sec squared x all over the bracket to the power of 2. And you can't do anything more than that, so we'll just leave it as it is. Part 2 then asks you to find the equation of the tangent to h of x at 0, 0. Well, to find the equation of a tangent, you need a slope and a point. I have the point, I just need to get the slope. So this was my slope down here. I now need to find the slope at x equal to 0. So I'm going to sub in everywhere there was an x, I'm going to sub in 0. Alright, just be careful, put it all into the calculator then. You should get out a slope of 1. So at the point 0, 0, the slope is 1. Then you go off and you get your equation of the tangent. Question 13. The function f of theta is equal to a third sine 3 theta plus 3 sine theta is defined for all theta is an element of the real numbers. Find f dash theta, the derivative of f of theta. Okay, so we'll go off and we'll do our derivative. So it's going to be 1 times a third is a third. Derive the function. Derive the trig function. So sine 3 theta turns into a cos 3 theta. And then derive the angle. 3 theta becomes 3. Over here then, 3 sine theta, it's going to become 1 times 3 is 3. Reduce the power by 1 and you'll get a power of 0. So sine theta to the power of 0 is just 1. And then derive the sine function, you get cos theta. Derive theta, you'll get 1. So it tidies up to be 3 cos theta. Okay, if you weren't able to follow what I was saying there, it's 3 sine theta. We want to derive it, so that's a power of 1. 1 times 3 is 3 by the bracket to the power of 0, multiplied by the derivative of sine function is a cos function. Sorry, cos theta, multiplied by the derivative of theta is 1. So that becomes 3 by sine theta to the power of 0 is 1 times cos theta by 1. That's 3 cos theta. Okay, tidy that up. So you've got a third cos 3 theta by 3. The 3's divide into each other and you just get cos 3 theta plus 3 cos theta. So that's the first part. Then it says, hence, find positive integers a and b such that the derivative of the function is a cos b theta. Right, so we're going to have to use our formulae from page 14 again in the log tables. Right, so we've got f of f dash theta was cos 3 theta plus 3 cos theta. We eventually want our answer to come out with a in front of a cos to some power of theta. Okay, so we're going to have to deploy some of our trig identities. Cos 3 theta, you will not get a cos 3 of an angle anywhere. So you can get a cos 2 theta, you can get a cos theta, so we're going to have to separate it out. Cos 3 theta could be rewritten as cos 2 theta plus theta. Okay, now isn't that a cos of an a plus b? Go into your log tables, page 14. Find the formula for cos of a plus b. Cos of a plus b, and I'm going to write it up here. So cos of a plus b is cos a cos b minus sine a sine b. Okay, that's what I'm now using here. So I'm substituting into that formula. So remember, your a was going to be 2 theta and b is going to be theta. So you get cos 2 theta cos theta minus sine 2 theta sine theta, and then I bring down my plus 3 cos theta. Next, you know you don't want to have any sine in your answer, but you also know you don't want to have any 2 thetas in your answer, okay? Because we eventually want to just get an angle on its own. So you look into your log tables and you find a formula for cos 2 theta, all right? Cos 2a is the formula you're looking for, and that will give you back cos squared a minus sine squared a. All right, so I've underlined cos 2 theta here, and I'm substituting in that formula for it. Cos squared theta minus sine squared theta, and now I have an angle on its own. I've gotten rid of that 2 theta. That is being multiplied by cos theta outside of it. Now, if you look in the log tables, you want to get rid of sine. So I've got a sine 2 theta. Alright, so sine 2 theta is the same as 2 sine theta cos theta. Here, so I've substituted in for that, and that is being multiplied by sine theta there. Then I bring down my plus 3 cos theta. So slowly but surely we're getting there, okay? We're going to try and get rid of our sines. Now I'm going to multiply out these brackets here, so I'm just going to delete all of these rules, or these lines, sorry. Okay, so I'm multiplying out that bracket, and you're going to get cos cubed theta minus cos theta sine squared theta. Okay, the rest then tidies up. Sine theta there by sine theta is sine squared theta. So that's minus 2 sine squared theta cos theta plus 3 cos theta. Next, every single term, there are 4 terms there all together in this line. Every term has a cos theta in it, so I'm going to factor it out, because I eventually want to get a theta on its own anyway. So I'm factoring out cos theta, and I open up a bracket. Cos theta goes into cos cubed theta, cos squared theta times. Cos theta goes into minus cos theta sine squared theta, minus sine squared theta times. Cos theta goes into minus 2 sine squared theta cos theta, minus 2 sine theta times, and cos theta goes into plus 3 cos theta plus 3 times. Now I'm going to tidy up inside that bracket. You've got a minus sine squared theta and a minus 2 sine squared theta. That's minus 3 sine squared theta. Okay, so it's cos theta, a bracket, cos squared theta minus 3 sine squared theta plus 3. We all know sine squared theta can be rewritten as 1 minus cos squared theta, and that's coming from these rules here from page 13 of the log tables. Okay, just by rearranging them. So now I've gotten rid of sine out of my formula, alright? So inside the bracket now I've got cos squared theta minus 3 plus 3 cos squared theta plus 3. The 3's cancel each other out and they're gone. You're now left with cos squared theta plus 3 cos squared theta inside the bracket. They're like terms, add them together, you'll get 4 cos squared theta. Lastly, multiply it back together. You're going to get 4 times cos cubed theta. And now you have it exactly as they wanted you to write it. A times cos theta to the power of b. So a is obviously 4 and b is obviously 3. They said find positive integers a and b such that f dash theta equals a cos theta to the power of b. So there is a lot in that question 13, but it's all coming from your use of the trig identities, right? So make sure you have all of that question down into your copies, line by line, and make sure you understand where everything came from. Question 15. Given that f of theta equals sine theta plus pi cos theta minus pi, find the derivative of f of theta and express it in the form of cos n theta, where n is an element of the integers. Okay, so straight away you can see this is the product rule, okay, u by a v. So let u equal sine theta plus pi, and let v equal cos theta minus pi. So again, put down your formula for the product rule, u dv d theta plus v du d theta. Okay, and over here on the right hand side, you can see what I'm getting out here. So u is equal to sine theta plus pi, therefore du d theta is going to be cos theta plus pi. V is equal to cos theta minus pi, therefore dv d theta, so we're differentiating v with respect to theta, is minus sine theta minus pi. Sub it into your formula. Okay, so sub it in over here. You'll get out the following line. Tidy it up. Okay, and now if we just rearrange the formula so that we can resemble some trigonometric identity inside in page 15 of the log tables, okay, or 14 or 15 of the log tables. So if it's rearranged, we can rearrange it as cos theta minus pi, cos theta plus pi, minus sine theta plus pi, sine theta minus pi. Okay, so we can let the first angle theta minus pi, let that be A. Let this one be B, okay? And here, over here, you can see we have A again, and this one was B. Okay, just so that the angles are the same in both brackets. So we're looking for the formula cos A, cos B, minus sine A, sine B. Alright, and if you look into page 14, you'll see that that's the formula for cos of A plus B. So we know that A is theta minus pi and B is theta plus pi, so just sub it into that formula. You're going to get the cos of theta minus pi plus a bracket theta plus pi. Tidied up, and you'll see that the pi's cancel each other out. Sorry, the pi's cancel each other out, and you are left with, sorry, over here, squeeze it in, cos 2 theta. Okay, and that's how they asked you to write your answer. They said write it in the form of cos n theta, where n was an element of the integers. Well, n is 2, obviously, here. Question 16. Let y equal 1 minus cos x all over 1 plus cos x, and show that the derivative, dy dx, will equal t plus t cubed, where t is equal to tan x over 2. Okay, so basically we want to eventually have a tan in our answer so that we can substitute in t for tan of x over 2. So anyway, we must go off and get dy dx. So this is the quotient rule, okay? You've got a u over a v. So u is equal to 1 minus cos x, v is equal to 1 plus cos x. So u is 1 minus cos x, therefore du dx is going to be, well, 1 goes to a 0. Then you've got minus cos x. So the derivative of minus cos x, minus stays outside the bracket. The derivative of cos x is minus sine x, and a minus by a minus is a plus. So du dx is sine x. Then v is 1 plus cos x, so get the derivative of that. The derivative of 1 is 0. The derivative of cos x is minus sine x. So dv dx is minus sine x. Sub it into the formula. So dy dx is going to equal v du dx minus u dv dx all over v squared. Multiply out the top line, alright, and you'll get sine x plus sine x cos x plus sine x minus sine x cos x. And you'll see that the sine x cos x cancel each other out. You're then left with sine x plus sine x, which is 2 sine x. Sorry, it's just cut off at the bottom there, but it's 2 sine x all over the 1 plus cos x all to be squared. Okay, so it's all over that denominator there. I just can't fit it in. Okay, so now you are looking at what you've just gotten your derivative to be. So 2 sine x all over 1 plus cos x all to be squared. Now you eventually want to have tan in your answer. So look into page 14 of the log tables and try and find a formula that has sine, 2 sine of the angle, or else a sine of the angle that has a tan in it as well then. So you can substitute it in instead of the 2 sine x. And if you look there, you can see that sine 2a is equal to 2 tan a all over 1 plus tan squared a. Okay, so just observe this. So the formula in the log tables is sine twice the angle is equal to 2 times tan of the single angle all over 1 plus tan squared of the single angle. Well, we've got twice the sine of the single angle if you look over here. This is what we were left with our derivative. Okay, so we've got twice the sine of the single angle. Well, then if we use that formula over on the right hand side over here and we try and manipulate it so that it looks like what we have. So they have sine of twice the angle is equal to 2 times the tan of the single angle. Well, then if we only have sine of the single angle, that'll be 2 times the tan of half the angle. Okay, so that's where I'm getting this from. Okay, so it's the sine of the single angle should equal twice the tan of half the angle all over 1 plus tan squared half the angle. Okay, hope that makes sense. So we can now substitute in for 2 sine x. Okay, so we now know that sine x will equal this here. That's what sine x will be. But remember, we had a 2 sine x. So there's my 2. And this is now where I'm substituting in for sine x. So sine x is 2 tan x over 2 all over 1 plus tan squared x over 2. And then we do the same on the bottom. Okay, so we have a 1 plus cos x all in a bracket to be squared. So again, if you look at page 14 of the log tables, and you can see that your formula is cos 2a is equal to 1 minus tan squared a all over 1 plus tan squared a. Well, we have a cos x, okay, or a cos a. So again, if it's cos of twice the angle is equal to 1 minus tan squared the single angle, well then all we'll do is we will half the angle again. So cos of the single angle then should equal 1 minus tan squared of the single angle all over 1, or sorry, the angle over 2, all over 1 plus tan squared the angle over 2. Okay, half the angle. And we can then substitute this in for cos x. So underneath we've got 1 plus cos x all to be squared. That's what this is over here. So we're substituting in. So it's a big bracket. 1 plus. This is now my cos x. Okay, I'm substituting in for cos x. And it's all in a bracket to the power of 2. Okay, next we are going to tidy up the numerator and the denominator. So up on top I'm going to multiply in by the 2. And you'll get 4 tan x over 2 all over 1 plus tan squared x over 2. Okay. Underneath then, I'm going to square out that fraction. Alright. Or sorry, no, I'm not squaring out the fraction yet. Sorry. I'm writing it as a single fraction. So I've got 1 plus 1 minus tan squared x over 2 all over 1 plus tan squared x over 2 inside the big bracket to the power of 2. So I'm going to write all of this as a single fraction first before I go squaring it out. Okay, so the lowest common denominator is obviously 1 plus tan squared x over 2. This is 1 over 1. So 1 into 1 plus tan squared x over 2 goes 1 plus tan squared x over 2 times. Multiply it by 1, so it stays as it is. Bring down your plus. Okay, so there's my plus. 1 plus tan squared x over 2 goes into the bottom once and multiply it by what's on top, which is 1 minus tan squared x over 2. Okay. Now we are just going to tidy that up a little bit further before I go squaring it out. You've got a 1 plus a 1, which is a 2. Then the tan squared x over 2's, they cancel each other out. So that cancels with that. So you're left with 2 all over 1 plus tan squared x over 2. Okay, it's kind of been cut off down here. But so it's 2 all over 1 plus tan squared x over 2, all to be squared. Okay, the top now is fine, 4 tan x over 2 all over 1 plus tan squared x over 2, but if we look at the bottom, we still have to square out that bracket. So it's the bracket by the bracket, okay, so top by top, so 2 squared is 4, and just leave the denominator to be squared. We're not going to square that out until we need to. Okay, so leave it all over 1 plus your tan squared x over 2, all to be squared. Alright, it's just cut off over here, but that's what's underneath. Okay, so now I've got a fraction divided by a fraction. So again, I'm going to flip it, invert it, and multiply it. Okay, so here is I've left the numerator as it was. It was 4 tan x over 2 all over 1 plus tan squared x over 2. And I'm multiplying it by the reciprocal of the denominator. So turn the denominator upside down and multiply it. Okay, so off we go. So the top by top, bottom by bottom. Now, so when we multiply the top by the top, just leave it as the bracket by the bracket to be squared, all over the bottom multiplied by 4. Okay, straight away, because everything up on top is being multiplied together, I can divide by the 4s, so the 4s are gone. Next, you'll see 1 plus tan squared x over 2 is common to both the numerator and the denominator. So up on top, 1 plus tan squared x over 2 to be squared, that goes into the bottom, 1 plus tan squared x over 2 times. So up on top, we are left with tan x over 2 by 1 plus tan squared x over 2, all over 1. Okay, now we can multiply out the top, and we'll get tan x over 2 plus tan cubed x over 2. Now we're nearly finished. The last thing said, let t equal tan x over 2. So if t is equal to tan x over 2, we can just sub in. So you're going to get, this is t, and because this is tan cubed x over 2, well, this will be t cubed. And you have now written it in the format they wanted it. They said show that dy dx is equal to t plus t cubed. So we have it shown. Alright, so if I just go back to the beginning again. So this was one of those, quite a tough proof, okay? So they gave the original function which had cos's involved in it. They said show that the derivative is t plus t cubed, where t is equal to tan of x over 2. So straight away that's telling you, you want to just have tans in your final answer. So you go off and you get your derivative first using the quotient rule. You'll get down as far as you can with simplification, and you get your 2 sine x all over 1 plus cos x all to be squared. So at that point then you're saying to yourself, right, I need to find some formulae in the log tables that has tans in it. So you're trying to get rid of that sine x up on top and replace it with a tan. And the only formulas that you can see on page 14 of the log tables where you have a sine x or a sine something is equal to tans is that sine 2a formula. Okay, and the same applies for the cos x function. The only cos x or cos a function that you can see on page 14, which has tans in the answer, is the cos 2a formula. Okay, and then you just go from there. But you have to recognise that the angles were slightly different in what you want. So you had the sine of a single angle, but the formula gives the sine of double the angle. So just always make sure that your angles are accurate when you're substituting in for formulae from the log tables. Right, the angles have to be the same, so that might mean you have to manipulate the formula in some way, and if that's the case, do. Or maybe the signs are different in some way, so that might mean you have to factor out a -1 or something like that to make them look like the formulae in the log tables. Okay, so that's differentiation of trigonometric functions. Okay, quite a long video. Make sure you've gone through every single one of these questions to make sure you have the answers out, particularly the ones that involve the use of trig formulae or trig identities from the log tables.